the way to sustain.
Microwave noise. Once the enemy of qubits and coherence is now their refrigerator. Superconducting quantum computers operate at temperatures extremely close to absolute zero, typically in the millikelvin range, achieved using dilution refrigerators. At these temperatures, quantum coherence can be preserved long enough to perform computations. In our previous videos, we saw that quantum states are extremely fragile. Even small disturbances like heat, vibrations, or electromagnetic interference can disrupt coherence and reduce reliability of quantum operations. Because of this, noise is normally treated as something to be eliminated. But researchers at Chalmers University of Technology, Sweden, have demonstrated something remarkable. They built a superconducting quantum device where engineered microwave noise assists heat transport, allowing the system to function as a quantum refrigerator. Let's understand how this works. The artificial molecule. At the center of the experiment is a superconducting circuit made of two coupled qubits. These are fabricated superconducting circuits designed to have discrete energy levels, similar in a way natural atoms possesses. Because of this quantized behavior of mimicking the atoms, they are often referred to as artificial atoms. When two such qubits are coupled together, they form what researchers call an artificial molecule. This molecule acts as the working medium of the thermal device.
Two microwave reservoirs.
The artificial molecule is coupled between two microwave environments. One acts as a cold reservoir, one acts as a hot reservoir. These are implemented using microwave waveguides with different effective temperatures. The molecules can exchange energy with both.
Controlled noise injection.
Now comes a key idea. A third microwave channel injects engineered dephasing noise into the system. To understand why this matters, let's briefly recall how coherence works. A qubit in superposition can be written as the phase phi determines the interference behavior. We can represent this state using a density matrix. Here, the diagonal elements, modulus of alpha square and modulus of beta square, represent populations, the probabilities of measuring 0 and 1. The off-diagonal elements represent coherence, the phase relationship between states that represent the entirety of all possibilities.
The core of quantum computing.
In normal quantum computing, uncontrolled noise reduces the off-diagonal elements. This process is called decoherence. When the off-diagonal elements go to zero, the system behaves like a classical mixture that is usually harmful. Uncontrolled noise reduces the off-diagonal elements towards zero. That destroys interference. This is decoherence. But in this refrigerator experiment, the noise is spectrally engineered. It introduces controlled phase randomization, meaning the diagonal elements, the populations, remain largely intact. The off-diagonal elements, coherence terms, are modified in a controlled way. Importantly, the noise does not randomly flip qubit states. It does not significantly disturb the energy populations. Instead, it slightly weakens phase coherence. Why is this useful? In a perfectly coherent system, certain energy transitions can be restricted due to symmetry and selection rules. When coherence is slightly reduced through controlled dephasing, some previously suppressed transition becomes allowed. Additional energy transport pathways open up. This enables noise-assisted quantum transport. In the refrigerator setup, controlled loss of phase coherence allows excitations, the heat quantas, to move from cold reservoir artificial molecule to hot reservoir. The molecule acts as a transport bridge. It does not accumulate energy, it facilitates directional energy flow. This is refrigeration driven by engineered dephasing.
Clear analogy.
Imagine the quantum state as a landscape. The peaks represent populations, the diagonal elements, the outputs. These determine what we measure when we read the qubit. The plateaus represent coherence, the off-diagonal elements, the whole superpositioned data. These encode interference and phase relationships. Now the controlled noise is introduced, but instead of flattening the peaks, it gently blurs the plateaus. The probabilities, the peaks remain sharp, but the phase relationships, the plateaus become slightly randomized. Why does this help? Because perfectly flat plateaus can restrict certain transport processes. By gently replacing plateaus, the system gains access to new energy transfer routes. Heat can now flow from the cold reservoir into the artificial molecule and then into the hot reservoir. The molecule does not collapse into classical behavior. Its energy structure remains intact. Only the phase coherence is adjusted just enough to enable heat flow. Energy is extracted from the cold reservoir and delivered to the hot reservoir. As this continues, the cold reservoir loses energy, the hot reservoir gains energy. This establishes refrigeration inside superconducting circuit. The researchers also demonstrated that by tuning system parameters and noise properties, the same device can operate as a refrigerator, a heat engine, a thermal accelerator. What this means? Precisely, this does not mean noise generally improves quantum computing. Uncontrolled noise still causes decoherence and computational errors. What this experiment shows is more specific. When noise is engineered and controlled, and when its spectral properties are carefully tuned, it can assist quantum thermal transport. In this context, partial phase randomization enables functional energy flow without destroying the system's essential structure. This work demonstrates controllable quantum thermal motion inside superconducting circuitry, practical implementation of noise assisted transport, experimental progress in quantum thermodynamics, potential future strategies for localized heat management in larger quantum processors. It triggered a powerful laboratory research, but it represents an important experimental advance. Quantum coherence is essential for computation, but this experiment shows that carefully engineered defusing, controlled modification of phase coherence can assist heat transport inside quantum circuits. This is a precise and experimentally demonstrated example of noise being used constructively in superconducting quantum systems. When the noise that was thought to destroy the quantum coherence could be engineered to improve the quantum systems and enhances its superconductivity, what barriers could the engineering and science break through? The expanding universe may have several consciousness scattered along itself, but let humanity be the primary decoder. Let's question deeply, let's explore, let's innovate to sustain. Don't forget your formalities to our channel. Nandri, Vanakkam.
Innovate to sustain.